continue from last lecture. The next topic we're going to discuss here is still chemical energy, is still regarding delta H, okay, and this one is standard heat of formation. We use delta H sub F standard to represent it. Yeah. All right, so first of all, what is this? Okay, and so far, whenever we talk about delta H, we say delta H is the enthalpy change of a given chemical reaction. Okay, delta H seems like it always relates to a particular chemical reaction. Okay, and a chemical reaction, of course, would involve a bunch of different chemicals. Okay, reactants, products, and now the standard heat of formation, though, although it's still regarding the enthalpy change of a particular chemical reaction, but mostly people tie standard heat of formation to an individual chemical compound. So this is for each compound. And actually, if you get your hand on a chemistry handbook, or if you look at the appendices of any chemistry textbook, okay, you should be able to find in the appendices a list of standard heat of formation for common chemical compounds. And you would see each chemical formula is followed by a standard heat of formation. Okay? And why is this? Why is it tied directly to a chemical compound? Okay, and how do you make sure that it's still a delta H about a chemical reaction? Well, let's take a look at the definition of standard heat of formation. This is the enthalpy change for the formation of 1 mole of a substance in its standard state from its elements in their standard states. Okay, so now you guys know me. I'm not going to ask you to memorize definitions. Okay, there's really no point. But you got to understand what this means. Okay, so by this definition, delta HF is still the enthalpy change of a reaction. The formation here, we're talking about a formation reaction. Okay, but this is forming specifically just 1 mole of a given compound in its standard state. Okay, and what would form this compound? Well, so this is your product, and from means this is your reactants. Okay, so this is the process, this is the reaction that we make 1 mole of a compound out of its own elements. All right, so let's see some examples. Okay, now what's the chemical compound we deal with the most? Well, obviously, it's water. Okay, so what is this reaction for water that's defying standard heat of formation? Well, first of all, that means the product, now since we're talking about the formation reaction, okay, the product is this 1 mole of substance, so 1 mole of water. Nothing else. Okay, and also this 1 mole of water is in its standard state, so let's label the state. What's the standard state for water? Well, standard state for water is liquid. Okay, now from its elements, what are the elements of water? Well, obviously it's hydrogen and oxygen. But these elements need to be in their standard states. What's hydrogen's standard state? Well, hydrogen's standard state is hydrogen gas, H2 gas. Okay, so H2 and gas. Okay, what's oxygen's standard state? It's O2 gas. Okay, so you're making 1 mole of this compound. Now, and of course, as a formation equation, you still need to balance it. Okay, now normally we would do this. We would put in 2 moles of this, 1 mole of oxygen, and 2 moles of water. And you've seen this reaction many times. But in this particular situation, for the formation reaction, you can't do that, actually. Why? Well, 1 mole. Remember? You're not making 2 moles of water. So what do I do? Well, you have no choice. You're only making 1 mole of water. Okay, that means you only have 2 hydrogens, so you only have 1 H2. Well, so what do I do with the O2? That's 2 oxygen there. Okay, well, 1 mole of oxygen contains 2 moles of oxygen atoms, and I only need 1 mole of oxygen atoms, so I can only use half of a mole of O2 gas. And you look at this, you go, didn't you tell us we need to use whole numbers as coefficients for balanced chemical equation? Yes. Okay. Not in this particular situation. Okay. Why? Well, because this is a formation reaction. This has already defined how much stuff you can do. Okay. Why do you have to define it as 1 mole of stuff? Remember, this is about delta H. Delta H of this reaction is defined as standard heat of formation of water, okay? But you also know the delta H values are tied in a thermochemical equation, is tied to the coefficients of your balanced chemical equation, okay? 2 to 1 to 2 in this case is different with 1 to half to 1. Okay? Because remember, if you double this, you have to double that delta H value. And you're going to have a different standard heat of formation value. That's why, okay? You can't change the coefficients of a standard heat of formation, a formation equation, because whatever change you make to your equation, okay, you have to change your delta H. We talked about that last class. Okay, so this would be the formation equation of water. Okay, and we explained the way of doing this for a pretty long time. Okay, but once you understand this, writing formation equation is actually pretty easy, pretty straightforward. Okay, for example, what about sodium chloride? What's the formation equation of it? Okay, formation equation of a compound is always about making 1 mole of that compound. So product is always easy. Just write that chemical formula, no coefficients needed, and that's the only thing on the right side. Okay, and this is standard state, and the standard state for sodium chloride table salt is a solid. Okay, and then it's going to be made by its elements, so sodium and chlorine. Okay, sodium is a metal. Okay, the standard state, and metals you don't need to form molecules, you just need the atomic symbol. That's good enough. And metals, aside from mercury, every other metal is a solid, so in its standard state, so put solid there. And then what about chlorine? Chlorine, like all the other halogens in the same group, okay, always make diatomic molecules, so Cl2 gas. Chlorine is a gas, okay, and then you got the same issue, like this is 2 moles of chlorine atom, and I'm making 1 mole of this salt, so I only need 1 mole chlorine, so I need half mole of chlorine gas. So put them together, that would be your standard formation equation of sodium chloride. Okay, and both of these two formation equations for water and for sodium chloride, okay, when you write it out, you realize that both of these two reactions could happen. Okay, burning hydrogen in oxygen makes water. We already know that one. Okay, if you put sodium metal and chlorine gas together, okay, you will ended up making sodium chloride salt. Okay, but not all formation reactions are actual chemical reactions that happens. Okay, what do you mean? Well, every chemical compound, you know that with what we've written down, with the way of writing formation reaction, we can create a formation reaction for it. Okay, let me give you this example. So let's say I have iron carbonate. Okay, this is a insoluble salt, whatever, but it's a chemical formula, common ionic compound. Okay, so what's the formation reaction for this guy? So making 1 mole of iron carbonate, iron 2 carbonate. This is a salt, so its standard state is solid. It's made up by 3 elements. Okay, iron, carbon, and oxygen. Iron is a metal, so atomic symbol, put solid on there, you have 1 mole of it, so you're good. Okay, carbon is a solid, and you don't need to worry about, we use the atomic form of carbon atom. Okay, and what about oxygen? Okay, oxygen is O2 gas, and how many? I need 3 moles of oxygen, so okay, 3/2 moles of O2 gas. So break it down to elements, find your standard states of elements, get your numbers straight and your physical states straight. You would get a formation reaction for iron 2 carbonate. But let's use red pen. This, you can write an equation like this. Okay, you can write an equation for every single compound's formation equation. Okay, but this is not a real reaction. What do you mean? You can put iron, carbon, and oxygen gas together all you want. Okay, so far right now, people don't have a way to turn these 3 things together, providing a certain condition, and turn it completely into iron 2 carbonate. It just won't happen. Okay, now, well, okay, so every compound I can write a formation reaction. Okay, but all those different formation reactions, only some of them are real, and actually majority of them are hypothetical reactions. Then comes the question, why the hell do I bother? Why do I want to go through all the trouble, write a reaction that doesn't exist? Okay, now here's the point of this. Here's why this is important. Here's why people are actually doing this. Okay, although most of the formation reactions are not real chemical reactions. Okay, the reactions themselves are not as important. The delta HF is important. What do you mean? By writing this hypothetical formation reaction, we defined the concept of delta HF. Okay, what good does this do? This made sure every chemical compound really could have a delta H value relate to it. We talked about it earlier. Okay, and why do I need a delta HF standard value for every compound? Because this is going to make your life much, much easier in calculating delta H of a new reaction that you created. What do you mean? Yeah. Remember, okay, delta H is a state function, okay? And we already talked about Hess law, which essentially says it doesn't matter how you get from the reactants to products, okay? Regardless of what routes you take, eventually, as long as you go from these reactants to these products, your delta H is a fixed value, okay? It doesn't matter which routine you take, okay? So now, tell me, what can delta H do for me? Well, delta H can give you this important way of calculating a chemical reaction. Because once you defined the standard delta HF for every chemical reaction, you're actually creating a way to calculate delta H of any given chemical reaction much easier. Because the delta H of any given chemical reaction should equal to the total, the sigma here means total, of all delta HF standard for the products minus the total of all the delta HF standard of the reactants. Now, think about how we get chemical reaction delta H before. Okay, how did we get this before? We showed you the two ways that we know at this point. One way is that, okay, I'll go get a calorimeter, I'll get all the chemicals I need, I'll make them into solution, I'll make a chemical reaction happen in the calorimeter. Okay, and then of course I better have a good thermometer taking all the temperature. I better know, the mass of everybody, all the solutions, how much water is involved, and so on and so forth. And then we can use the insulated system equation, the delta H plus Q equal to 0, to figure out delta H. Okay, so that's one way of doing it. Okay, so far we have two ways of calculating delta H. One, so delta H calculation method. Right now, we have one experimental method with calorimetry, where we use delta H plus Q equal to 0, and then we do all the measurements, all the experiments, then we figure delta H out. So that's one. Number two, obviously, is the Hess law. Okay. Now, using thermal chemical equations of related chemical reactions. Okay. All the rearrangements, turning things, and manipulating the equation, manipulating delta H value, and eventually add things up. That's Hess law. Okay. So these are the two ways that we know so far how to calculate delta H. Both of them are pretty complicated. Okay, so the first one you're going to have to do experiments. You're going to have some equipment. Okay, and you're going to be able to do a bunch of complicated calculations because the Q need to be broken down. There's so many things involved. All of that. Okay. And Hess law method, although you don't require a chemical experiment, well, you do have to find a whole bunch of related reactions. And depending on how complicated the equation that you want is, okay, if it involves, let's say, 10 reactants, 12 products, you're going to need a whole bunch of related chemical reactions, okay? And so both of which are pretty complicated. But now, look at our method number 3. Use standard heat of formation of all components and the balanced chemical equation. Okay? Get all your reactants. Use your balanced chemical equation, however many moles of stuff, okay? If you have 1 mole, you use delta HF. If you have 2 moles, you use 2 moles times delta HF. Okay? If you have 3 moles, you use 3 moles times delta HF. Add all your products value together, subtract all your reactants, calculate the same way. Okay? So what do you need this time? You don't need an experiment. You don't need a whole bunch of related chemical reactions. You need a balanced chemical equation, which if you're studying a chemical reaction, you definitely have, and a chemistry handbook. Chemistry handbook with values of all delta HF of, chemical compounds. Which one are you going to pick if you're actually doing chemistry research and finding delta H of chemical reaction? Of course, method number 3. Okay? I don't need to design no experiments. I don't need to find research for a whole bunch of different chemical reactions. Give me a chemistry handbook, looking at the chemical equation. I can solve this in 5 minutes. Okay? So that's why this delta HF thing, okay, is important to us. All right, so before you use it to do any calculation, though, let's clear up a few things. Okay? Now, all the chemical compounds have delta HF value. What about these free elements in their standard state that you use for these equations? Okay, let's clear it up. Delta HF for all free elements. What is, oh, not free equation. What is free element? One element by itself. This. No charge. So all free elements in standard states we're defining their delta HF equal to 0 by definition. Okay? Now, why do you define it? Because there's no, again, delta H is a standard, is a state function. Okay? State function, we care about the difference. We don't know the absolute value. So for a individual free element, okay, because you can't write the formation equation of a free element. It has only one element, okay, and without that equation, we don't really have a point of origin, okay, in our system. This is by definition giving us a starting point, a point of origin, okay, in this calculation. Okay. So delta HF for all free elements are defined as number 0. And now, this is not saying free elements, okay, will have a potential energy, will not contain any potential energy. That's absolutely not what I'm saying here. They still have potential energy, okay? But what you need here is simply a point of origin, and a point of origin in a situation where you deal with a state function, okay, is really not that critical, okay, because you care about the difference between two things. As long as they start at this, like you said, let me give you this example. So let's say you're measuring some difference in lengths, okay. So let's say this one is from 0 to 5 centimeters. Another one, so length is 0, 6 centimeter. Okay. Now you set the 0 point here, okay, so, and then you measure it, okay, because you use the same starting point. Now, the two lines have length difference here. Okay, so let's see that clear. Okay, so the top one is 5, bottom one is 6. Okay, the difference between the two is 1 centimeter. So delta is 1 centimeter. Okay. What if I move the point of origin? What if I move the point of origin by 1 centimeter? Now it changed the length of each now if you set the point of origin here, now you only have 4 centimeter left or 5 centimeter left. Okay? But does that change the difference between the two? No. where you set up point of origin, okay, doesn't change the difference between things in the same system. Where you set the point of origin, okay, as long as you have the same point of origin, okay, then it doesn't change state function. It doesn't change delta H. We just need a point of origin, that's all, to get a value. Okay, so anyway, now you don't have to memorize all this. Okay, this is all explanation if you're really sinking into this, trying to understand why and how does this work. Okay, now for Chem 115, you don't really, there are things that you don't really need to know how and why does it work, okay, to still be able to deal with them and perform in your exam, in your quizzes. Okay, now if you want to know why, you want to know how, I'm going to try my best to provide you with that information, with that knowledge. Okay, but if you don't need to know and you don't want to know, like, okay, you can know, okay, this for all three elements in standard states, their delta HF is defined, is by definition 0. So if I see in a chemical reaction in the future, there's a free elements in its standard states there, okay, if I need to do this calculation, I'll just take the delta HF value of those free elements as 0 and plug them in. I can do my calculation. That's good enough. Okay, now, so after all these explanations, okay, let's see an example. Let's say I have a chemical reaction here, C2H5OH alcohol. Okay, let's say it's in liquid state, reacting with oxygen gas, produced carbon dioxide, yes, and liquid water. Okay, now, this is just burning of alcohol. Now, if we know that for each compound they have these particular delta HF value, now, and delta HF has the unit of kilojoule per mole. Okay, C2H5OH has delta HF of negative 277.8 kilojoules per mole. Liquid water has negative 285.8 kilojoules per mole, and carbon dioxide has negative 393.5 kilojoule per mole. If we know all these, calculate the delta HF of, oh no, not delta HF, calculate delta H of the reaction. Okay, so what do I do? Delta H should equal to total of all delta HF of products minus total of delta HF of reactants. So products are carbon dioxide and water, so let's go. Carbon dioxide is negative 393.5 kilojoules per mole. Okay, and don't forget, I have 2 moles of this sun, okay? Because standard heat formation by definition is making 1 mole of stuff, right? That's where the per mole is coming from. But I have 2 moles of it, so this is going to cancel mole, give me kilojoule. Okay, well, I don't need the parentheses here. Okay, plus 3 moles of water times negative 285.8 kilojoule per mole, so that mole cancels, minus 1 mole of alcohol, negative 277.8 kilojoule per mole, so that cancels, plus 3 moles of O2. Well, you didn't give me a delta H value for O2. Well, I didn't have to. Remember, oxygen all by itself, no charge. O2 is the standard state of oxygen. Free elements in their standard state has delta H of 0. Okay, so now once you have them all together, the calculation itself, I'm not going to bother that much. Negative 1366.6 kilojoules. And that would be the delta H, so you can write delta H standard of this reaction is negative 1366.6 kilojoule. And together, this would be a good thermochemical equation. And this also tells you why people use alcohol as a fuel. Burning 1 mole of alcohol would give you, theoretically, this much energy. Release negative delta H means exothermic reaction, so release a ton of energy to the environment. The more energy it can provide, the better fuel choice it can be. All right? So this is a normal standard operating procedure that people use to calculate delta H of a given chemical reaction, especially if you're not involving like new chemical compounds. If you're just having a chemical reaction with commonly known compounds that's in the chemistry handbooks. Okay, yeah, just look them up, get the delta H value. As long as your equation is correctly balanced, you're all set. So that's why we do this standard heat formation sign. Okay, now, all right, so the last thing we're going to do here is another example. Okay, so let's move this a little bit. Darn it. Just want to move this up. So that we can do a new example. And this is going to combine some of our previous knowledge together a little bit. Okay, calculate the standard heat formation of benzene C6H6 liquid if we know that two C6H6 reacting with 15O2 produce 12 carbon dioxide and 6 liquid water, and the delta H standard for that is negative 6,598 kilojoule. carbon dioxide gas breaking down to carbon solid and O2 gas. Delta H standard is 393.5 kilojoule, and 2H2 gas plus O2 gas producing 2 liquid water, and delta H equal to negative 571.6 kilojoules. Okay, now, so calculating the delta H or F of a given organic compound, okay, if we know these three thermochemical equations. All right, so first of all, let's analyze this question, okay? Calculate delta HF. Okay, so I can imagine a particular question that you can ask me about delta HF is, okay, give me a chemical reaction, give me the delta H value of it, and give me all the other components delta HF. Like you have 4 components, you gave me 3 of them, and you're asking me to calculate the last delta HF of one of the components. Okay, because I know the delta H should equal the total of products minus total of the reactants. I can set up that equation. I can figure out if there's an X in there. But you're obviously not asking me to do that because you didn't give me any other delta HF value. Okay, yeah. You gave me instead 3 known equations, known thermochemical equations. And I've seen this before. There is another example that you gave me a bunch of thermochemical equation. Okay, whenever you see a whole bunch of thermochemical equations, the first thing you should reflect in your head now is this a Hess law problem? Because Hess law is the only place we know so far that use multiple thermochemical equations. But if this is a Hess law problem, then we need a target equation. We have a bunch of known equations. We don't have a target equation. But hey, let me think about this. Delta HF for a compound. How did we define delta HF? Oh, for all compounds, there's a formation equation, isn't it? No, we don't have a target equation right now. But if it's about delta HF, I can always create one. What do you mean? I can always write the formation equation because it's about 6 carbon solid and 3 hydrogen gas. And the delta H of that should equal to delta HF of benzene. So if I use this formation equation and I figure out the delta H, I'm all set. So now I have a target equation. I have known equation 1, 2, and 3. Now let me see what I can do. Because now this is a Hess law problem. Okay, so first, carbon. Do I see carbon in here? Oh, carbon. Okay, carbon here is on the product side, and I want it to be on the reactant side. Okay, carbon is also in coefficient 1. I want coefficient to be 6. Okay, so what I'm going to do that, I'm going to need to reverse the second known equation so that carbon is a reactant, And then I'm going to need to time it by 6. Okay, so let's do that. If I do that, I would have 6 carbon, 6 O2, producing 6 carbon dioxide. Okay, and my delta H now, whatever due to the equation, due to delta H, so delta H is now negative 393.5 kilojoule times 6. So negative time reverse equation times 6. All right, so that took care of carbon. Hydrogen gas. Do I see hydrogen gas? Oh, I see hydrogen gas here. Okay, now, so what should I do? Hydrogen, well, it's on the same side, so great. Okay, I don't need to reverse nothing, but it's 2 and I want 3, so equation number 3 times 3/2. So the 2 would cancel and would turn into 3, so it's going to give me 3H2 gas, 3/2 of oxygen gas, and 3 water liquid. Delta H standard now, of course, is negative 571.6 kilojoule times 2/3. All right, so what about the last component? So we're following our Hess law method, looking at every component of the target equation, find them in the known equation, manipulate the known equation, and manipulate the known equation's delta H value. Okay, so the last one here is C6H6. It's obviously in equation number 1, but it's on the opposite side again. This I need it on the product side, it's on the reactant side, so I need to flip that. And then I also need to, okay, it's 2, and I want 1, so divide by 2. So reverse the first equation, divide by 2. Okay, you would have, okay, so the products becomes reactants, each divide by 2, so 6 CO2, 3 water, producing 1 C6H6 and 15/2 of O2 gas. And the delta H standard, of course, now is negative 6598 kilojoule times 1/2. All 3 components taken care of. Now we can add them up. Okay, so let's see. There's the carbon, there's the H plus, and that's 6 CO2, 6 CO2, 3 water, 3 water, 6 oxygen, that's 12/2, and then 3/2, that's a total of 15/2. Guess what? Oh. What did you get? 6 carbon solid, 3 H2 gas, and C6H6 liquid. What is that? That's my target equation. Since I added these 3 things to get the target equation, I should add this and this and this together. So add them all up. Okay, you get negative 393.5 times 6 plus 571.6 negative times 3/2, and then plus, oh, okay, negative sign need to be turned into positive sign, plus delta H becomes positive 80.6 kilojoule. And that, of course, is also the delta HF, because this is the formation equation of C6H6. So we practiced in this example both the concept of delta HF, writing a formation equation, and we also practiced on the previously learned Hess law problem solutions. And that's it for Monday's class. And we'll continue, and this is it for all the chemical energy stuff that we're going to be talking about in Chem 115. We're going to move on to a new chapter starting from Wednesday.